Hey guys, so in this video we'll be seeing how to calculate the gradients of the loss function with respect to the input parameters. So we are using a single layer perceptron for this example. So more generically you would have seen a single layer perceptron to be something like this. We have the features input layer here, and then we have one output layer. So this is the output. So this example is put in this diagram. So our main objective is to differentiate the loss function with respect to the input parameters. Let's get started. So as you can see, the input parameters pass through several functions to reach the loss function. So you would have to calculate the gradients of all these functions to be able to compute the gradients of the loss function with respect to W1. So to illustrate with an example, let's take W1. To compute the gradient of the loss function with respect to W1, you have to compute this function's gradient with respect to W1, which is dz by dW1, or you can call it dou. This is partial differentiation. And then after you compute dou z with respect to dou W1, you have to compute this function with respect to this. So that we have here. So in a similar fashion, you compute the loss function's gradient with respect to the sigmoid function A. So if you see this equation, this is all in multiplication, and if you cancel out these terms, dz, you will end up with dl by dW1, which is the final answer. So to compute the final answer, we have to get started from the reverse order. dl by dl, actually we don't have to compute dl by dl because differentiating a variable with itself always gives 1. So this is just for explanatory purposes. So yeah, we come back and differentiate the loss function with respect to the output of the activation function, which is A. This is where we are now, dl by dA. So let's compute dl by dA. So the loss function is minus y log A minus 1 minus y log 1 minus A. So when you differentiate these two with respect to A, so let's split these two like this and differentiate each of the term with respect to A. When you differentiate this with respect to A, you get minus y, which is considered to be a constant because these two are in multiplication. And then we have to differentiate log A with respect to A. So log A by dA is 1 by A, and then you have to differentiate A with respect to dA, which is 1, like how we saw here. So this portion is over. Now coming to here, we have a similar term which is in multiplication, so you write it as it is and differentiate log 1 minus A with respect to A. So this gives you 1 by 1 minus A, this differentiation, and then the last term 1 minus A with respect to A. So this is same as writing diff d by minus 1 into A by dA. So this gives you minus 1, so into minus 1. So we have this term here. Now let's simplify it a bit more. So this is minus y by A, and this is minus minus plus, so 1 minus y by 1 minus A. These two are in addition. So this is the final term. Okay, now since we have computed the final term, we can actually write it in the main sheet. So it is 1 minus y by 1 minus A plus minus y by A. So this is dl by dA. So now since we got dl by dA, we can come back and cross this over. We got dl by dA. Now we have to compute dA by dz. So now we are calculating differentiation of the sigmoid with respect to z. So what is sigmoid? Sigmoid is 1 by 1 plus e power minus z. So this can also be written as 1 plus e power minus z to the power minus 1. Rewriting it, we have differentiation of 1 plus e power minus z to the power minus 1 with respect to z. So we are differentiating this whole term now. This equals minus 1 plus e power minus z to the power minus 2. Alright, now the whole term is done. Let's come inside. Differentiation of this with respect to z is 0. Differentiation of this with respect to z is e power minus z. And we have one more z term here. So we have to differentiate this with respect to z, which gives you minus 1. Now to simplify the whole equation, you have something like e power minus z by 1 plus e power minus z the whole square. So this is the final answer, but we don't like it this way. So let's simplify it. I'll get rid of this for a while. So the final term was e power minus z by 1 plus e power minus z the whole square. So this can be rewritten as 1 by 1 plus e power minus z. We got our a. And then e power minus z by 1 plus e power minus z. So we have a and we have this complicated term. We don't want this to be this complicated, so we reduce it. So how to reduce it? You can see e is common in both the numerator and the denominator. So you add 1 and then subtract 1. So this way this becomes 1 plus e power minus z by 1 plus e power minus z, which is 1, and then this portion is over, and then we are going for this portion, minus 1 by 1 plus e power minus z. So this is minus a. So combining the three, we get this to be equal to a into 1 minus a. So this is the final answer. So now since we have computed this, we can update it here. So we are done with dl by dA. We are done with dA by dz. So let me grab this from here and write it here. 1 minus y by 1 minus a plus minus y by a. So we have this huge term here, and then this we just computed to be multiplied by a into 1 minus a. Cool. So we have the second term and the third term. To compute the third term, dz by dw1. So dz by dw1. So whenever we are differentiating a function with respect to a variable, the variable is always in the function. So the function is w1 x1 plus w2 x2 plus b. Now differentiating this function with respect to w1 will give you x1 here, 0 here, and then 0 here. So this is simple. This is just x1. And then to differentiate w2 with respect to z, it follows the same principle, only that we have x2 here and rest are 0. So what we do now is, for w1 we multiply it by x1. So now we have the 3 terms that we want. Let's simplify. For now I'm going to take these 2 terms, so 1 minus y by a into a by 1 minus a. We can cut these 2 a's in a similar fashion. 1 minus a into 1 minus a, cut. So this gives you 1 minus y a, and then in the same way plus, you can cut these 2 a's off, minus y by a into 1 minus a. So cut these 2 off, you'll be left with this term. So it is minus y plus ya, and we have this term here. So simplifying it a bit more, you get a minus ay plus ay gets cancelled. Now cancel these 2 and we get a minus y. So we have a minus y, and then we have this x term, so into x1. This is the final answer. Now writing it here, dl by dw1 is equal to a minus y into x1, and dl by dw2 can be written as a minus y into x2, and dl by db can be written as a minus y, and we don't have any term here, so it's cool.
So previously we had 2 features, x1 and x2, and we had the parameters w1, w2 and the bias b, and we computed dou L by dou W, which is the differentiation of the loss function with respect to weight 1, weight 2 and then the bias. So we got these 3 parameters. So this case is when the number of examples is 1. So what if we have different examples? We have many examples in the training set. For example, we have m to be like 2 or 3. So when m is 2, we have one set of x1, x2 which belongs to the first example, and another set which belongs to the second example, like this. So we have the second example like this, which follows the same parameters. So when we have 2 examples, we compute the differentiation of the loss function with respect to w1 in the first example in a similar way, and the answer is right here. We have a minus y into x1. So x1 does play a part in determining the gradient of the loss function of the first example with respect to weight 1. Similarly, x2 will play a part in determining the gradient of the loss function of example 1 with respect to w2. So when we have a different example, x1 and x2 varies, right? So similarly, we'll have a different set of parameters, different set of gradients for the second example. So similarly, if we have many examples, we will have many of these stacked up like this. So we'll have many of these stacked up like this, and you can see the L1 with respect to W1 is common, L1 with respect to W2, L2 with respect to W2. So the weight isn't updated yet. We are just finding the gradients of each of the example. What we do after computing the gradients for all the examples is that we take an average. We take the average of the gradient of the loss function with respect to W1, and then we subtract it from the weight and then update it. So we update it for all the examples, and then repeat the process over and over again, so that the rate of change of the cost function is minimum.